So, we have seen generalized coordinates helps us a lot in terms of reducing the number of independent variables to exactly match or rather reducing the number of coordinate to match exactly the number of independent variable required. And so, what we can do is we will try to express the D'Alembert's principle, which is given as m d or rather m x I double dot minus or rather sorry my mistake, which is given by f I applied minus p I dot into delta x I equal to 0, and of course, there is a summation over I. So, we would like to write please remember that these x i's are not generalized coordinates. These are the standard Cartesian coordinates, could be Cartesian coordinate, could be any of the standard coordinates, but there are total of 3n of these guys. So, this summation goes from 1 to 3n, right. Now, what we need to do is we need to reduce this number of independent, I mean we will try to write this equation in terms of 3n minus k, which is equal to n number of independent variables which are given as q1, q2, qn, the so called generalized coordinate. So, our next goal would be to reduce this D'Alembert's principle in terms of this equation, I mean this quantity, so that please remember the advantage what we will gain if we can write in terms of this generalized coordinate, each of these coefficients will be individually equal to 0. If you recall, we discussed this, we have C1 x 1 plus C2 x 2 plus C3 x 3 all the way up to Cn x n equal to 0, if and only if x 1, x 2, x n are independent, we can write C1, C2, Cn individually equal to 0. So, this is something that is from the linear algebra, and I am pretty sure you are familiar with this concept. If not, you can always check your linear algebra textbooks and class notes, and you will definitely find this there. Now, so what I am trying to tell you is, if we can write these equations in terms of we can convert this D'Alembert's principle in terms of these independent coordinates, then we can individually equate each of these coefficients to 0. But before that, it turned out there is another way of doing it. Okay. So, we have 3n number of these guys, and we have k number of constraint equations of the form phi alpha is equal to phi alpha of x 1, x 2, x or rather x 3n. For any holonomic constraint, could it be rheonomic or could it be scleronomic, does not matter. The constraint conditions can be written in form of an equation that we have seen. That is the definition of a holonomic constraint. Also, there is an explicit, I mean in general there is a time dependence, depending on whether we are dealing with scleronomic constraint or rheonomic constraint. This time dependence could be explicit or implicit. But anyway, this is the most general form for a system with holonomic constraint. So, this is for holonomic. And so, okay. So, this is sorry, it is a slight mistake here. So, the constraint equation is actually this equal to 0. So, this is the general form. If you recall, we have equations of the form x square plus z square equal to L square when we were solving simple pendulum. By the way, if you recall, in the last lecture we could not locate a minus sign, the origin of a minus sign. That was because we took z equal to L or z nearly equal to L towards the end, it has to be z nearly equal to minus L, because we are working in right hand coordinate system. So, this is x, if this is x, z has to be like this. What I did was I took the z along this direction, which is wrong. So, this is actually minus z. So, we have to take z equal to minus L, which will solve the minus sign problem. Anyway, apart from that, the equation of constraint is x square plus z square equal to L square. So, what we can do is we can take it in this side and we can write it as x square plus z square minus L square equal to 0. So, this in principle is our constraint equation of the form t equal to 0. There is no time dependence here, but in principle these quantities x and z, they can vary as a function of time. So, we will put it in this way. Now, so the general constraint equation has this particular form. I will just write it once again. So, phi alpha, alpha runs from 1 to k, k being the number of constraint conditions. Okay. So, it will be x1, x2, x3n equal to 0. So, we are, if you recall, in the last class itself we said we are not writing R1, R2 components of R1, R2 and R3 Rn independently, separately. So, instead of writing x1, x2, instead of writing x1, x2, x3 or x1, y1, z1, x2, y2, z2, we are writing x1, x2, x3 up to x3n. So, this is something that we have adopted as in we, instead of writing x, y and z, we are just writing one index x. So, if we have alpha of such equations, it is obvious that d of phi alpha will be equal to 0, because this side is 0 anyway. Okay. Now, d of phi alpha in its most general form has this this nature is del phi alpha del x I, where I runs from 1 to 3n dxi plus del phi alpha del t, which is once again, so it is 0. So, put the 0 on this side, right. What I did here is simply we have taken the partial derivatives of this relation. There is a t here. So, it will be the partial derivative of each individual coordinate and a partial derivative due to time. Now, if I convert this relation in terms of virtual displacement of this constraint condition phi, that means instead of writing d phi, if I simply put d delta as in curly delta phi alpha, which is a symbol for virtual displacement, what happens is the first term stays as it is, except we have, what change we have is this d is also replaced by delta xi, right. So, this and this term, and there is a dt, sorry, del I del t dt equal to 0, right. So, what happens to this term? This term goes to 0 as delta t for any virtual displacement is equal to 0 unanimously, right. So, this is the constraint equation, or this is a straightforward outcome of the constraint equation, is this equal to 0. Okay. If you, I hope you understand this partial derivative I have taken. If it is a function of, let us say, x and z. So, if phi is equal to x, z and t, okay, so we have to write d phi equal to del phi del x dx plus del phi del z dz plus del phi del t dt. Okay. So, we just use that, all the coordinates are put into this sum and times were there, which we set equal to 0. Okay. Now, what we can do is, there are alpha I mean there are k number of such equations, right. So, what we can do is we can multiply each of this relation, each of this k number of relations with some constant alpha, or rather some constant lambda. We can multiply this with some lambda alpha, which will be equal to a lambda alpha here, right. So, this is some arbitrary constant, and this will also be once again will be equal to 0. So, what we are doing is we are simply writing this as lambda alpha delta phi alpha, which is also equal to 0, because multiplying anything with 0 is 0. So, now what we can do now, because this is a null quantity, as in it is the total value of this quantity is 0, we can always go back and add this number of all the equations in this form into this D'Alembert's principle. So, what I am trying to tell you is we can rewrite D'Alembert's principle as f I a minus p I plus sum over alpha lambda alpha del phi alpha del x I whole into delta x I equal to 0. So, that could be an alternative form of D'Alembert's principle without losing any generality. What I am trying to tell you is this is valid and this is also valid because of this relation. These are essentially, this summation is 0. Okay. But then please remember that there are k such summations, and the bane of this equation was we have 3n number of parameters in D'Alembert's principle, but actual independent parameter is n is equal to number of independent parameter is equal to 3n minus k. So, if I can somehow get rid of k number of equations from, or k number of relations from this by the way, I am just switching to Einstein's summation convention. As I is a repeated index, the summation is implemented over I, right. So, I am not writing it explicitly. I mean, it is very difficult to write summation every time. So, we will just follow the summation convention. Okay. So, this means there is a summation over I. Now, the situation is following. We have n number of equations, 3n number of equations, out of that only 3n minus k numbers are independent parameters. So, a rest k number of equations, what I can do is I can set okay, let's look at it this way. Let's say we have a series like this C1 delta x1 plus C2 delta x2 up to Cn delta or C3n delta x 3n equal to 0. We have an equation of this form. Now, because x1, x2s are not independent, we cannot say that C1, C2, C3 up to C3n vanishes independently. But if we can adjust our this alpha sorry lambda such that out of this total number k number automatically vanishes. Now, this please remember this alpha is an arbitrary lambda is an arbitrary constant. So, we can check the values of this to the actual real value of this quantity, and we can adjust this quantity such that the total sum vanishes. We can do that in principle. So, if that we do such that k number of coefficient automatically vanishes, then we are left with 3n minus k equal to n number of coefficients, which are exactly same as the number of independent parameters. So, from this full set of 3n coordinates, we can easily say that out of these 3n coordinates, 3n minus k numbers are anyway independent, because that is the number of independent parameters. So, rest we can just manipulate this this quantity and or these quantities rather, okay, and we can say that they are independent, right. So, if this is the case, if we can we can set them equal to 0. So, if this is the case, we can essentially say each of these parameters of C1, C2, C3 which has this particular form up to C3n, they are all equal to 0 individually. Out of them, please remember, out of that total number of coefficients which has this particular form, we are making k number of coefficients equal to 0 by adjusting this arbitrary constant, and the rest are becoming independent as we are setting and that will match exactly, sorry, the rest are independent because they are matching exactly the number of independent parameters or independent coordinates. And so, overall what we have is totally 3n number of equations of this particular form equal to 0. So, this is a way of separating out coefficients from this particular equation. Okay. So, it is a modification of D'Alembert's principle. This particular, the way of modification is we multiply this with a constant, as a certain constant condition we multiply with a constant and add with the original equation. This multiplier is called Lagrange's undetermined multiplier, Lagrange's undetermined multiplier, and this equation, the final equations we get, they are called the Lagrange equation. I think I can write here, right. So, they are called, this family of equation is called Lagrange's equation of first kind. So, this family is called Lagrange's equation of first kind, and this particular lambdas which are the undetermined constant are called Lagrange's undetermined multiplier. I am pretty sure you have used Lagrange's multiplier in different for your maths problems. Sometimes you have a constraint equation, you have to solve two equations in a particular, I mean under certain constraint condition, and this is where we use Lagrange's multiplier in general. That is where it was first introduced sometime in 1750s. I do not remember the exact recall the exact date and time. Lagrange, Joseph Louis Lagrange, he was a famous he was a young mathematician at that time. He found this out, this phenomena, that actually D'Alembert's principle can be used. I mean directly from D'Alembert's principle we can make all independent equations by applying an undetermined multiplier. And I think somewhere around 1755 or something, that time he was not even 20, he wrote a paper and sent it to this famous most famous mathematician of his time, Euler. Now, Euler immediately saw the potential in this, and he actually, so he appreciated his work, and not only that, he started developing on this, he started building on this platform, and essentially what we got is the Euler's equation of second kind, or Lagrange equation of second kind, or the Euler-Lagrange equation. That we will do in a moment. Okay. But before that, we will just take up this problem of simple pendulum once again, but this time we will be using Lagrange's undetermined multiplier. In the last class, what we did, we started with D'Alembert's principle. We wrote wrote D'Alembert's equation for simple pendulum, and under certain assumptions. So once again, in writing D'Alembert's principle was never good enough. We had to use the constraint condition somehow in order to gain, in order to separate, or in order to make this get an independent equation of motion from equation of this form. Now, what we are going to do is we will explicitly use this constraint condition to separate out two equations. Okay. So, once again, simple pendulum has constraint condition of the form x square plus z square minus l square equal to 0, right. So, there is only one constraint equation, So, this is a good, that means we do not have any sum. This sum actually goes from I equal to 1 to k. We do not have to apply this sum. So, there are two independent variable, or rather two parameter x, two variables x and z, and one constraint equation, which will effectively reduce it to a single constraint equation, a single parameter equation. Right. Now, if I apply this derivative, del phi del x is equal to 2, right, del phi del z is equal to 2, okay. And of course, there is no explicit time dependence, so we are not anyway bothered about this. So, and please recall now, understand that these are independent standalone equations for each of these parameters. So, sorry, this is a pi dot, this pi dot can actually be written as mi xi double dot, right. So, these are equations of xi only, right. So, for simple pendulum, we can write two equations of the form, for x there is no force. So, the force which is acting, so this is my m and this is my L, that is the length, okay. This is my support. So, whatever force is acting in the z direction mg, right. So, f x is equal to 0 and f z is equal to mg, right. So, this is my x and this is my z and this is minus z, right. So, if I write my first equation for x, it will be 0 minus m x double dot plus lambda times del phi del x, which is 2 lambda equal to 0. Second equation will be mg minus mz double dot plus 2 lambda is equal to 0, right. Okay. So, we got two equations which we can now what to do. Okay. So, once again we have to make this assumption that z double dot is equal to but 0, but that comes later. First of all, we okay. So, we have two equations with whether the one way is we have to determine lambda from this to solving this, I mean from somewhere. So, we have one constraint equation here which is explicitly used, or what we can do is we can just subtract one equation from the other and get rid of the lambda. So, either way this is a valid thing, because these two equations are valid. So, whether we can get a value of lambda and substitute it, or we can just get rid of the lambda from two equations, that is up to us. So, let us do this in the other way. So, we have minus m x double dot plus 2 lambda minus mg minus mz double dot minus 2 lambda is equal to 0. Now, if we do that, 2 lambda goes, and if we put z double dot is equal to 0, once again we have a sign issue. How can, sorry. So, this will be, oh, it's terrible mistake. So, it will be 2x and 2z, that makes more sense. So, we have a 2x here, lambda, yeah. So, 2 lambda x and 2 lambda z, yeah. Now, this makes more sense, right. So, in the first term we have to add del x del xi del phi del xi, right. So, first equation will be x 0 minus m x double dot plus 2 lambda x, right. Okay. So, now these are two equations, right. Okay. So, if these are my equations, what I can do is I can, from the second equation, once again I can put z equal to minus L and z double dot is equal to 0. If I do that, what I get is 2 lambda minus 2 lambda L, or 2 lambda L is equal to mg. So, that will give you lambda equal to mg by 12. Okay. So, essentially we are not eliminating lambda, but we are getting a value for lambda. Now, if I, that is from the second equation. Now, if I put it back in the first equation, I get is, so it will be lambda on the other side, right. So, it will be mx double dot plus 2 into mg by 2 Lx is equal to 0. 2 goes, m cancels, which will be x double dot plus g by Lx is equal to 0, right. So, we got back the standard equation for simple pendulum, again under this set of approximation, right. This approximation we have to do, because otherwise if we do not make this approximation, our pendulum is not simple pendulum and this equation is not valid. So, okay, so I made some initial mistakes by just omitting this derivatives, but this is the general procedure, sorry. Okay. Now, although this is a very elegant method of solving or getting insight into the system, or essentially getting back the equation of motion. So, what is the advantage? First we have to discuss. The advantage is we are not worried about the constraint forces. Okay. Not worried about constraint forces means we are simply writing the force as it is, like we are writing mg here instead of taking the component. And on the other hand, we have a disadvantage, because this formulation, whatever, I mean, it might be elegant compared to what we have in D'Alembert's principle. It is very difficult for larger systems to, every time if we have, see, in this case we have one constraint equation. We can have systems which actually have 4, 5, 6 constraint equations. Now, gaining this, or so what we have to do is we need to put 5, 6 different values of undetermined multiplier lambda, and in effect we have to solve for these multipliers. This is a very tedious process and sometimes it is not very elegant. Okay. So, that is why it will be even better. And so, what we are doing essentially, we are starting from the standard coordinates, Cartesian coordinate systems, and we are ending up also equations, writing equations in terms of Cartesian coordinates. Right. I mean, not that the Cartesian, I mean, I should not say Cartesian coordinates, or rather I would say we are sticking to the old coordinate system in this method. But we have already defined a set of generalized coordinates which are exactly the number of, which are as many in number as required by the system for a complete description. So, it is always better if we can write this in terms of independent parameters, right. So, let us try that, and these are, as this one is called Lagrange equation of first kind, the one we are going to derive now is called the Lagrange equation of second kind. Okay. Now, Lagrange equation of second kind, right. So, we start with the, okay, I think we have to remove this because we need this space. So, we start with this term here. So, we have, forget about the minus sign, we have pi, or rather I would write mi del, not del, dx dxi dt2, right, times delta xi equal to 0. So, if I just, or sorry, I should not write equal to 0. So, this is the second term, right, and there is a summation over I, right. Now, if we start playing with this second term mathematically, what do we get? It's just basically a mathematical series of mathematical manipulation. Okay. Let me just have a look at it. Right. So, what we can do is we can write this in terms of, so okay, this part is a bit tricky and I always need to refer to my notes because there are so many calculations. Instead of this curly xi, what we can do is we can convert it in terms of the generalized coordinate. We have to add another sum. This operation I will justify now. Remember, there were these transformation equations. We wrote as R1 equal to R1 of Q1, Q2, Qn, n is equal to 3n minus k. So, first of all we will change R to x because we are not using R's anymore. Sorry. Similarly, we have x2 is equal to x2 of what not. Similarly, we have xn is equal to x or x3n is equal to x3n of what not. So, if we look at the ith coordinate, ith Cartesian coordinate, which is again a function of q's, right. Now, if we take dxi like we did for in case of constraint equations, we can show that delta xi, I am just not repeating this calculation, delta xi is nothing but del xi del qk delta qk, where sum is over k. So, we just did that. Additionally, there is a sum over k. Once again, we do not have to write any of this explicitly. Why? Because both the indices k and I, they are repeated index, and a repeated index, if in Einstein's summation convention, means that the summation is implemented. So, we will be following the simpler form. We will not write the summation explicitly. If this index is repeated, for example, here I is repeated, right, k is repeated. So, we assume. Okay. What do we have? So, I hope you understand this, why we changed delta xi to this. Now, let us see. If I have a quantity of the form ddt of mi ri double dot, right, ddt of mi ri double dot, right, sorry, okay. This is, I will just simplify it even more. So, I will just put double dot here. So, it is mi xi double dot del xi del qk delta qk, right. So, now this it can be shown with simple simple mathematics, that this is equal to ddt of mi xi dot delta xi delta qk minus delta xi delta qk minus mi ri dot, and this third term will be delta, yeah, it will be ddt of del ri del qk. Okay. This can be, I mean, again, it's looks very straightforward. There are some tricks in it, because please remember that the derivative is also running over all the summations, summation over k and I. So, it is bit tricky, but it is nothing impossible to show. It is not very complicated, but we have to be careful. It is not very straightforward as it might look like. Okay. So, this is equal to this. It can be shown. There are two or three steps in between. I am just omitting that. I am leaving it to you. Now, there is another thing I would like to point out. dxi is equal to del xi del qk dqk plus del xi del t dt, right. So, if I from here, if I try to write the total time derivative, which is dxi dt, which is xi dot, this will be this and this will come down, right. So, xi dot is equal to del xi del qk dqk dot del xi del t. From here, if I take another partial derivative of this velocity with respect to a generalized velocity. Okay. So, if qk is a generalized coordinates. So, the velocity qk dot, the total time derivative of a generalized coordinate, is a generalized velocity. Okay. And there is a reason why we can treat generalized coordinates and generalized velocities as independent parameters. Why so? Because you just take an example. Let us say velocity in a central orbit. What happens? A particle is moving in a central orbit. So, we need to specify its position as well as one of its velocity in order to get the full description. So, although velocities are velocities are function of position, the time derivative of position, it is purely not the position alone. A time derivative essentially means it is a division by one variation in the coordinate and one variation in the time. So, it is not only a velocity, although it is a dependent, it is a function of a position, it is not only the position, what I mean to say is it is not sufficient if you only specify the position of a particle to get the full description. In order to gain full insight, you need to have both information of a position and a velocity. So, that is why generalized velocities and generalized coordinates, they can be treated independent of each other. Okay. Now, if I try to take partial derivative with respect to a generalized velocity, it is this one. Okay. What we gain is del x del q k dot is equal to del x dot del q k dot is equal to del x I del q k. So, this is an interesting result, keep this in mind. Okay. This is, you can in short you can call it the cancellation of dots. It is as if we are dividing these two quantity and these dots are getting cancelled. It is not that, strictly speaking it is not that, but it is easy to remember that when we are dividing two quantities, the dots are getting cancelled. And it is true for any other parameter, which in this case we are just taking the time derivative of Cartesian coordinate. But even for a constraint condition, for example, if a constraint condition is also a function of velocity, we can do the same treatment. We will use this relation later on. Okay. So, this is one relation that we need to keep in mind. So, now using this relation, if I change this, if I put two dots here, it will be a valid modification, and readily I can show you that this quantity is nothing but partial derivative of total kinetic energy, which has the form T is equal to half m I V I square. Now, xi dot is nothing but Vi. So, I can write this as Vi, right. Right, and T is half mi Vi square. Now, a good thing about energy is these are frame invariant. If we change from Cartesian coordinate to generalized coordinate also, the velocity or the total form of kinetic energy does not, I mean the value of kinetic energy does not change. So, we can use a kinetic energy which is defined in terms of Cartesian coordinate in this equation and take a derivative with respect to generalized coordinate. It will not alter the problems. It will physically, it is a valid description. Okay, so we will start from here. So, we see the first term reduces to time, I mean a partial derivative of time, sorry, kinetic energy, and the second term is what we need to see, and we will find out what is the final form of Lagrange equation of second kind in the next lecture. Thank you.